Hello, welcome again. We are solving some questions of fluid mechanics and machinery. The topic is hydraulic machine. Question number 28 is the degree of reaction for any hydraulic turbine is given by equation R is equal to 1 minus V1 square minus V2 square divided by 2GHE, where V2 absolute velocity of water at exit, V1 absolute velocity of water at inlet, He change in total energy per unit weight inside the runner. Then the Francis turbine with radial discharge and the degree of reaction in terms of angle is given by assume flow velocity to be constant. Option A, R is equal to 1 minus cot alpha divided by 2 uh, bracket cot alpha minus cos theta, and B, R is equal to 1 minus tangent alpha divided by 2 tangent alpha minus cot theta. C, R is equal to 1 minus cot alpha divided by 2 tangent alpha minus cot theta. Uh, D, R is equal to 1 minus cot alpha 2 cot alpha minus tangent theta. So where alpha is inlet guide blade angle and theta is inlet moving blade angle. So as degree of reaction is given by this 1 minus V1 square minus V2 square divided by 2G He. So as the discharge is given radial for positive turbine with radial discharge, so it means beta is 90 and there is no valve component at outlet. So it means Vf2 is your radial velocity, and it is also given that flow velocity is constant. Okay, so Vf1 is equal to Vf2. Okay, so it means there is no radial beta is 90 or there is no tangential component of velocity at outlet. Okay, so He is your change in total energy per unit weight inside the runner, or it is the head that is utilized to generate power. Okay, so that is given by 1 by G VW1 U1. So this is the uh, power generated within the turbine per unit weight of per unit discharge. Okay, so as VW2 is 0, so this will be actually it is VW1 U1 plus VW2 U2. So as VW2 is 0, so it is VW1 U1 1 by G. So this is per unit mass uh, power. Okay, okay. So that is VW1 U1, and this is your inlet velocity diagram. This is your V1, this is alpha, this is your VR1, this is your VF1, and this is U1, this is VW1. Okay, so V1 has two components, VW1 and VF1, and this is the inlet blade velocity. So this is your relative velocity at horizontal component of relative velocity, and this is vertical component of vertical velocity. So VW1 is your VF1 cot alpha, or VF1 by VW1 is your tangent alpha. So VW1 will be VF1 cot alpha. So converting this VW1 and U1 in terms of VF and alpha. So V1 is sorry. So VW1 is your V1 VF1 cot alpha, and U1 is, because here there is VW1, that we have converted as VF1 cot alpha, and U1 is VW1 minus VW1 minus U1 that sorry U1 is VW1 minus V1 cos alpha, VW1 minus VF1 cot theta, this value VF1 cot theta. So U1, this is U1 plus this component is VW1. So if we subtract this amount from VW1, we get U1. So VF1 cot theta, if we subtract from VW1, then we get U1. So this is your U1. So VW1 is your VF1 cot alpha, putting here, and this is your VF1 cot theta. Now we have VW1 and U1 in terms of VF1 and cot. Okay, Uh, so He will be your 1 by G, putting the value of Bw1, that is this quantity, and U1 this quantity. So He can be written as Bf1 square by G cot alpha minus cot theta into cot alpha. If we take Bf1 as common, so it will be Bf1 square, and this is cot alpha. So now V1 and V2 in terms of Bf1 and alpha. V1 and V2 in terms of Bf1 and cot alpha. So we have write out this V return U1 now, V1 and V1 and V2. So V1 is your VF1 cosecant alpha, and as VF1 as V2 is your as star is radial, so V2 is your VF2, or VF2 is your VF1. So we can write this also. So now we can put the equation of derivative reaction. So that is your Bf1 square cosecant square alpha. Okay, and this is your Bf1 square. V1 is this and V2 is this, and He is this. So here it is 2G and it is 1 by G. Bf1 square cot alpha minus bracket cot alpha minus cot theta, or it is 1 minus cosecant square alpha is your cosecant square alpha minus 1 is your cot square alpha. So it is cot alpha. So cot alpha minus cot theta. So cot alpha will cancel out. So it will be 1 minus cot alpha by 2 cot alpha minus cot theta. So answer will be option B.